In this lesson, we will be starting the electricity unit, Unit 6. In this lesson, we will be covering the concepts of electrical charge and the force acting on electrical charges. So to begin with, all electrical charges come from the atom. In nature, atoms are normally found with an equal number of positive and negatively charged protons and electrons, making the atom neutral. But when there is an imbalance of charge, we get a net charge on the atom. If there are extra electrons, it becomes negatively charged. If there are electrons that have been removed, it becomes positively charged. The amount by which it becomes positively or negatively charged is dictated by the number of electrons that are added or removed. Every electron has the same charge, which we use the lowercase letter e to represent. That is known as the elementary charge. We can represent that as an equation, Q equals NE, where Q is the net charge on the atom or the material, and N is the number of electrons that have been added or removed, and E is the elementary charge on one electron. Some basic masses. Because protons, neutrons, and electrons all do have mass, by gaining or losing electrons, we can actually add and remove mass to our system. The elementary charge is a value of 1.6 times 10 to the negative 19 coulombs. Coulombs is just the unit that we're going to be using for charge. A lot of times we'll represent charge in terms of coulombs, but sometimes we'll use microcoulombs or even nanocoulombs. So knowing your metric prefixes is very important. Here's a question: how many electrons are there in 1 coulomb of negative charge? Here we have our equation, Q equals NE. Q is going to be our 1 coulomb of charge, N is going to be the number of electrons we're trying to find, and E is our elementary charge of 1.6 times 10 to the negative 19 coulombs. We can plug these into our equation. 1 coulomb equals N times 1.6 times 10 to the negative 19 coulombs. This gives us a value of 6.25 times 10 to the 18, and this should not actually be coulombs here. It's just the number of electrons. A person scuffing her feet on a wool rug on a dry day accumulates a net charge of negative 42 microcoulombs. How many excess electrons does she get? And by how much does her mass increase? Here's another question that we are going to use the elementary charge, but since we are talking mass, we're also going to need the mass on an electron. We're going to use the same equation, Q equals NE. Q, however, this time is going to be negative 42 times 10 to the negative 10 to the negative 6. Micro means 10 to the negative 6, so I can simply replace micro with times 10 to the negative 6. Equals N, some number of electrons, times the elementary charge. You'll note that the elementary charge here is given as a negative because we have negative charges and we are talking about electrons. I can use this to find out how many electrons there are with simple division, and then I can take that number of electrons and multiply it by the mass on one electron to find the value by which her mass has increased. Insulators and conductors. This is just some basic information that we need to know about these different kinds of materials before we can move on. A conductor is any material that allows charge to flow freely. Typically, metals are going to be our classic examples of conductors. And insulators are materials that allow almost no charge to move through them. Typically, rubber is a very good insulator, plastics are good insulators, wood is another example of a good insulator. So here I have an example of a charged object, this one is positively charged, and a neutrally charged object. When I place a piece of metal across the two, positive charges can flow from this object into that object. However, when I place a piece of wood across the top, no net charge can flow. This does bring us to the law of conservation of electric charge. This is a corollary of the law of conservation of matter. Law of conservation of matter says that we cannot gain or lose mass. It only changes form. The law of conservation of electric charge says that we cannot gain or lose charges. They will only move from one object to another, assuming that our system is isolated. We'll talk about the triboelectric series in a minute. So an example of the law of conservation of electric charge would be if I rub an ebonite rod against a piece of animal fur, the ebonite rod gains negatives because the animal fur loses those negatives and becomes positives. You'll notice that for every positive gained on the animal fur, I have a negative gained on the ebonite rod. This method of charging is known as charging by friction. Anytime you rub two different materials together, there's a strong possibility that you could gain a net charge on one or the other. The likelihood of it becoming positive or negative is dictated by its position on the triboelectric series. This is just a description, a qualitative description of how likely it is that a material will become positive or negative when charged by friction against another material. So if I'm looking at animal fur and ebonite rod, I would classify animal fur as being similar to wool, because wool is an example of animal fur. An ebonite rod, that is a kind of plastic that's a kind of plastic rod, so I might think of it as being maybe polyethylene or vinyl. The ebonite rod is down here becoming more negative. The fur is up here becoming more positive. It is important to note that when an object becomes negative, it is because it is ripping electrons off of the other object. The next method of charging is called charging by conduction. It is when the transfer of electrons is facilitated by direct contact between the two materials. You typically need to have conductors for this to happen. Here we have our neutral metal rod, and I bring into contact with it a charged metal object. The neutral metal rod will become positively charged because it is in contact with this charged metal object. You could think of these positives as moving onto this neutrally charged rod. But in reality, it is electrons that are moving in the opposite direction. We can also charge something by induction. This is a method used to charge an object that is not in contact with a already charged object. So here we have a neutrally charged object, and this one is actually connected up to this symbol here, which represents ground, which is literally the ground. The ground is a source of can act as a source or a sink for charges. If I have extra charges, they will run into the ground. If I need extra charges, they will come from the ground. This is actually an example of when our system is not isolated because it is connected to the ground, and the ground here is actually literally the earth. If I bring a negatively charged object nearby, positive charges are going to aggregate near that negatively charged object, and negative charges are going to get repelled down into the ground. If I were to then cut this wire here and disconnect from the ground, I would be left behind with a positively charged object. The electroscope is a device used to determine what kind of charge you have, or if you have a charge. It is made of an insulating case with a metal rod that runs down, connected to two thin pieces of metal, typically gold, although sometimes it is aluminum or copper. If you have an electroscope that is already charged, if this is already charged, let's say it is already positively charged, the positive charges would be evenly distributed along the entire length of it. And we could use that to determine the sign of an unknown charged object. So in this case, I'm using a negatively charged one. I have extra negatives. They're evenly distributed throughout the entire material. You'll notice down here, they're on both of the pieces of foil. If I have negative charges close together, they will actually repel away from each other. If I bring another negatively charged object nearby, it will take all the negatives that were up here and push them away down into the leaves. So the leaves will now become more negatively charged and they will repel out even further. If I bring a positively charged object nearby, it will actually pull the negatives up to the top, trying to get as close to this positive as possible and cause the leaves to relax in. This is because opposite charges attract one another and like charges repel. These charges experience a force dictated by an equation known as Coulomb's law. The force along the line connecting the charges is attractive if the charges are opposite, and it is repulsive if the charges are the same. Here we have a diagram of two positive charges experiencing this repulsive force. We have F12, which is the force on 1 from 2, and F21, which is the force of 2 on 1. So object 2 pushes on object 1 pushes on object 2. According to Newton's third law, Every action has an equal but opposite reaction. These two forces are equal, but in opposite directions. Same is true if we have negative charges. And if we have positive charges, the only difference is they are an attractive force, but they are still equal, but in opposite directions. Coulomb's law is this equation here. The force can be calculated by taking k, which is a constant, multiplied by the two charges involved, divided by the distance between them squared. So this is the equation used to give it the magnitude of force between 2-point charges. Q1 and Q2 are the charges of the 2 points. Please note that they are multiplied together in the numerator. They are not added. The unit of charge is still coulombs. The proportionality constant K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. That is a constant on your reference table. Here's an example. Suppose that we have 2-point charges, one with a charge of 1 coulomb and the other with a charge of 3 coulombs, both positive, and they are separated by a distance of 2 meters. Determine the magnitude of the electrical force of repulsion between them. Here's the equation we're going to use, F equals KQ1 Q2 over R squared. We're going to plug in our numbers. K is that constant off the equation sheet. Q1 is going to be our first charge. Q2 is going to be our second charge. They get multiplied together in the numerator. In the denominator, we have our distance of separation 2 squared. When I plug these values in, I get 6.74 times 10 to the 9th newtons. Assuming you are using all base units, coulombs and meters, which you should always use, your answer will be in newtons. Here we have an example. 2 balloons are charged with identical quantity and type of charge, negative 6.25 nanocoulombs. Nano means times 10 to the negative 9th. They are held apart at a separation distance of 61.7 centimeters. Centi means times 10 to the negative 2. Determine the magnitude of the electrical force of repulsion between them. Now, even though this question only gave us one value for coulombs, we do have to remember that there are 2 balloons that are charged with an identical quantity. We're going to use our same equation. We plug in our numbers again, making sure to convert nanocoulombs into coulombs with times 10 to the negative 9th, and making sure to convert centimeters to meters with times 10 to the negative 2. And we get this value, 9.26 times 10 to the negative 7 newtons. That's going to do it for this lesson. There are a few worksheets that will be published about that we recommend you do on Wednesday or Thursday to help practice the stuff learned in these lessons. I would recommend that you maybe rewatch this lesson when it comes time for you to do those worksheets.